Hello everyone, welcome back. In our previous session, we laid the groundwork for understanding the forced vibrations. We explored how an external force acting on a system can lead to sustained oscillations. Today, we are diving deeper into a specific scenario, forced vibration with base excitation. This is part 2 of our forced vibration series. We will be building on the concepts what we covered in part 1. So, if you haven't reviewed that material, I highly recommend doing so. I am Dr. Sindamarikannan, Associate Professor in the Department of Mechanical Engineering at SVC, and I am excited to guide you through this fascinating aspect of vibration analysis. So, let's get started and explore the dynamics of force vibration with base excitations. Alright, let's take a quick look at what we will be covering in this part of forced vibration discussions. First, we will delve into the response of a damped system under the harmonic motion of the base. This is the scenario we introduced in the previous session itself, where the foundation of our spring mass damper system is oscillating. We will explore how the damping in the system affects the amplitude and phase of the mass vibration in relation to the base motion. We also deriving equations and examining the key parameters that govern this behavior. Next, we will move on to slightly different but equally important scenario, response of a damped system under rotating unbalance. This is a very common situation in rotating machinery where an imbalance in the rotating component creates a periodic force leading to forced vibrations. We will see how this type of excitation affects the system's response, and also we can analyze and mitigate the resulting vibrations. Both of these topics are crucial for understanding and controlling vibrations in various engineering applications. So let's get started with our first topic and explore the response of a damped system under harmonic based excitation. Let's take a quick look at our system. We have a mass M connected to a spring with stiffness K and a damper with damping coefficient C. Now, what makes this scenario unique is that the base of the system, instead of being fixed, it is undergoing a harmonic motion. This motion is represented by y of t equal to y sine omega t, where capital Y is the amplitude of the base motion and omega is its frequency. You can see this sinusoidal motion visualized here. The base is oscillating up and down with this specific pattern. This base motion in turn forces the mass m to vibrate. Our goal is to understand how the motion of the base influences the vibration of the mass. How does the amplitude and frequency of the phase motion affect the response of the system? We are now going to delve into the mathematical representation of the system behavior. Our goal is to derive equation of motion that describes how the mass m responds to the harmonic motion of the base. As we discussed, the base is undergoing a sinusoidal motion represented by y of t equal to y sine omega t. This motion is transmitted through the spring K and damper C to the mass m. To derive the equation of motion, we need to consider the forces acting on the mass. Here we have the inertia force, that is mx double dot, that is mass into acceleration, damping force, c times the relative velocity between mass and the base, which is x dot minus y dot, spring force k times relative displacement between the mass and the base, which is x minus y. Let's put all these terms in the equation by applying the Newton's second law. We see sum these forces and set them equal to 0. This gives us the equation of motion, that is mx double dot plus c times x dot minus y dot plus k times x minus y equals 0. Let's see what it is. Mx double dot represents inertia force. C x dot minus y dot represents damping force. K x minus y represents spring force. The equation is a second order differential equation that describes motion of the mass m under the influence of the base excitation. Understanding this equation is crucial for analyzing the system's response. In the next slides, we will further explain and explore the solutions of these harmonic motions of the base, and also we understood how the mass m vibrates in relation to the base motion. Now, let's take the equation of motion we derived in the previous slide and manipulate it to get a clear understanding of the system's response. We know that base motion is given by y of t, y sin omega t. We can substitute this in our equation of motion, that is this equation. After substituting and rearranging, we can get this equation in terms of mx double dot plus cx dot plus kx equals ky plus cy dot. We then substitute y of t and it derives y dot and use trigonometric identities to combine sine and cosine terms into a single sine term with a phase shift. This gives us ky sin omega t plus c omega y cos omega t, which can be expressed as a sin omega t minus alpha, where alpha is our phase shift. Here a represents amplitude of the forcing vibration and alpha is the phase angle. A is given by y times the square root of y times the square root of k squared plus c omega squared, and alpha is given by the arctangent of negative c omega over k. Now we are interested in the steady state response of the mass denoted by xp. This represents the long-term behavior of the mass after any transient effects which have died out. Through further mathematical derivation, we arrived at this expression. Here, psi is another phase angle given by the arctangent over k minus m omega square. This phase angle accounts for the difference in phase between the forcing function and the response of the mass. This equation for xp of t is crucial because it tells us how the mass will vibrate in response to the base excitation. It shows that the amplitude of the mass vibration depends on the amplitude of the base motion. the spring stiffness and damping coefficient, the mass and frequency of excitation omega. The phase of the mass vibration is also shifted relative to the base motion by angle alpha and pi. By analyzing these equations, we can understand how the system's parameter can affect its response and design the systems to minimize unwanted vibrations. Let's further simplify the expression for the steady state response we derived in the previous slide. We have this rather lengthy expression for x of t. While it's accurate, it's not the most convenient form for analysis and interpretation. Hence, we can rewrite this equation in a more compact and insightful form. That is, x of t equals x sine omega t minus phi. Here, we can able to represent x, the amplitude of the mass steady state vibration, and pi, overall phase angle. We also can express the ratio of amplitude x to the base motion y as x to the ratio of y, which is given by this expression. This is the original form of x by y, but we can further simplify it by introducing dimensionless parameters, which makes it easier to analyze the system's behavior. By expressing the equation in terms of frequency ratio R, which is omega by omega n, and damping ratio psi, which is C divided by 2 square root of mk, with this simplified form, more convenient for plotting and analyzing the system's response for different values of R and psi. Similarly, the overall phase angle can also be expressed in terms of dimensionless parameters R and psi, and we will get this simplified form. Let's see how this R and psi influences the response of the damped system. Now, let's visualize how the system response changes with respect to frequency ratio R and damping ratio psi. We will focus on the key concept called displacement transferability. It is nothing but x divided by y. The displacement transferability is denoted as T suffix d, which tells us how much the amplitude of the mass vibration x is amplified or attenuated compared to the amplitude of base motion y. In other words, it is the ratio x by y. Mathematically, we can express it as x by y equals Td, which is then further equal to the square root of 1 plus 2 psi squared times the magnitude of the frequency response function h of I omega. This equation highlights the dependence of transmissibility on both damping ratio and frequency ratio. Let's look at the graph on the left, which shows the displacement transmissibility as a function of the frequency ratio R for different values of the damping ratio. The vertical axis represents displacement transmissibility and the horizontal axis represents frequency ratio R. Each curve represents a different damping ratio ranging from 0 to 1. Notice how the shape of curve changes significantly with different damping ratios. For low damping ratios, that is psi closer to 0, we see a sharp peak near r equal to squared root 2. This peak indicates resonance, where the mass vibration amplitude is significantly larger than the base motion amplitude. As the damping ratio increases further, the peak became less pronounced and the transmissibility decreases. For high damping ratios, that is, psi close to 1, the transmissibility is always less than 1, meaning the mass vibration amplitude is always smaller than the base motion amplitude. Now, let's look at the graph on the right, which shows the phase angle psi as a function of the frequency ratio R for different values of the damping ratio psi. The vertical axis represents phase angle and the horizontal axis represents frequency ratio R. Again, each curve represents a different damping ratio psi. Notice how the phase angle changes with frequency and damping. For lower frequency ratios, that is R closer to 0, phase angle is closer to 0 degree, meaning the mass vibration is in phase with the base motion. As the frequency ratio increases, phase angle increases, reaching 90 degrees at R equal to 1 for all damping ratios. For higher frequency ratios, the phase angle approaches 180 degrees, meaning the mass vibration is out of phase with the base motion. These graphs are crucial for understanding how the system responds to different base excitation frequencies and damping levels. This allows us to design systems that minimize unwanted vibrations or to achieve specific vibration characteristics. Let's summarize the key takeaway we can glean from the displacement transmissibility graph we just examined. The observations are crucial for understanding the behavior of our system under base excitation. The very first observation is the value of transmissibility is unity at r equal to 0 and close to unity for small values of r. This means that when the excitation frequency is very low, closer to 0, or much lower than the natural frequency, the mass vibration amplitude is essentially the same as the base motion amplitude. The system is simply following the base motion without any significant amplification or attenuation. The second observation is for an undamped system, psi tends to 0 when transmissibility approaches infinity at resonance R is 1. This is a critical point in an ideal undamped system. When the excitation frequency matches the natural frequency, we get resonance. The amplitude of the mass vibration theoretically becomes infinitely large. Of course, in real world scenarios, there is always some damping which limits the amplitude, but principle of resonance remains important. The third observation is the value of transmissibility is less than unity for values of r greater than square root of 2 for any amount of damping psi. This is very useful observation. It tells us that for excitation frequencies significantly higher than the natural frequency, that is R is more than square root of 2, the mass vibration amplitude will always be smaller than the base motion amplitude regardless of the damping level. This builds beneficial for vibration isolation, where we want to minimize the transmission of vibrations. The fourth observation is transmissibility value is equal for all values of psi, that is damping ratio, at r is square root of 2. This is another intrinsic point. At a frequency ratio of such level, the displacement transmissibility is always equal to 1 regardless of the damping ratio. This means at this specific frequency, the mass vibration amplitude is exactly the same as the base motion amplitude, irrespective of any damping in the system. Alright, let's tackle a new problem together. We have a scenario involving a vehicle moving on a rough road. We need to determine the displacement amplitude of the vehicle. As the problem states, we have a vehicle with a mass of 1200 kg. The suspension system has a spring constant of 400 kilonewton per meter and a damping ratio of 0.5. The vehicle is traveling at a speed of 20 km per hour. The road surface varies sinusoidally with an amplitude of 0.05 meters and wavelength of 6 meters. Our goal is to find the displacement amplitude of the vehicle, which is essentially the amplitude of its vertical vibration. To do this, we will need to apply the concepts we learned about forced vibration with base excitation. First, let's identify the given parameters and convert them into consistent units. The mass is 1200 kg. Spring constant K is 400 kilonewton per meter. That we can write in terms of Newton per meter. Vehicle speed is 20 kilometer per hour. Let's convert this into millimeters per second. That is multiply by 1000 and divided by 3600. Then we get approximately 5.56 meter per second. The road surface amplitude y is 0.05 meter and the wavelength is 6 meter. Now we need to find the frequency of the road surface variation. We can do this using the vehicle speed and the wavelength. Let's take a closer look at the diagrams which representing the problem just what we discussed, that is vehicle moving on a rough road. This diagrams helps us visualize the problem and understand the forces involved. The diagram A shows a more detailed representation of the vehicle and the road surface. Here we can see the vehicle of a mass m moving horizontally with a velocity v in kilometers per hour. The road surface is depicted as a wavy line representing the roughness or irregularities of the road. This roughness is what causes the vehicle to vibrate vertically. We can see one complete cycle of this roughness, which corresponds to the wavelength of the road surface variation. The amplitude of the road surface variation is denoted by capital X or Y. In this case, we represented it by capital Y. This represents the maximum vertical displacement of the road surface from its mean level. The next important thing is the vehicle is modeled as a mass M and the suspension system is represented by combination of springs and dampers. We see two springs, each with a stiffness of K divided by 2 and a damper with a damping coefficient C. This configuration represents a simplified model of a vehicle suspension system which helps us to absorb the shocks and vibrations from the road. We have two vertical displacements indicated. X of t represents vertical displacement of the vehicle mass m. Y of t represents vehicle displacement of the road surface. The difference between this displacement is what determines the forces acting on the suspension system. Now, let's look at diagram B. This is simplified representation of the system focusing on the essential elements for our analysis. Here we have the mass M connected to a single spring with a stiffness K and a damper with damping coefficient C. This represents a simplified model of the vehicle suspension system where the two springs in diagram are combined into a single equivalent spring. The road surface variation is represented by a sinusoidal wave. This indicates that the road surface is varying harmonically with an amplitude y and an angular frequency omega. Again, x of t represents the vertical displacement of the vehicle mass. Y of t represents the vertical displacement of the road surface. Both diagrams represent same physical system, but diagram A provides more detailed view of the vehicle and the road surface, while diagram B simplifies the system for easier analysis. This sinusoidal representation in diagram B is particularly useful for applying the principles of forced vibration with base excitation, which I have been discussing. Let's continue solving our vehicle vibration problem. We have already identified the given parameters. Now we need to calculate frequency, natural frequency, and the frequency ratio. First, let's determine the frequency omega of the road surface variation. The problem tells us the vehicle speed v is 20 kilometers per hour. We need to convert this into radians per second. Let we use that omega equal to 2 pi f, and substituting this f is the frequency in hertz. We can express in terms of vehicle speed v and wavelength, which is 6 meters. After converting the speed to meters per second and substituting, we will get omega as 0.29 radians per second in terms of v. With v being 20 kilometers per hour, we find that omega is 5.8178 radians per second. Next, let's calculate the natural frequency of the vehicle suspension system. We know that the natural frequency omega n is the square root of the spring constant k divided by the mass m. We have k as 400 into 10 to the power of 3 newtons per meter and m as 1200 kg. Substituting these values, we get natural frequency equals to 18.25 radians per second. Now, let me calculate frequency ratio by substituting omega, forcing frequency, and natural frequency of the system, that is R equal to omega by omega n. Then the frequency ratio, what we got is 0.3186. Let me go for the next slide and continue the problem. Now, let me complete this vehicle vibration problem by calculating the amplitude ratio and displacement amplitude. We can find the amplitude ratio x by y using the formula that we discussed earlier in terms of psi and r. This formula relates the amplitude of the vehicle vibration x to the amplitude of the road surface variation y based on the frequency ratio r and the damping ratio. Let me substitute the known values. Whatever we calculated, R is approximately 0.318, psi is zero point 0.5. Substituting these values into the given formula, we can able to calculate the amplitude ratio, that is approximately equal to 1.1. Now we calculate the displacement amplitude of the vehicle, which we know that x by y is 1.1, and the road surface amplitude, which is nothing but y is 0.05. Substitute y as 0.05 meters. Therefore, we will get approximately 0.055 meters, that is 55 millimeter. What we observe? It is the meaning is 5 centimeter bump in the road is transmitted as a 7.3 centimeter bump to the chassis and the passenger of the cars. This result highlights the importance of understanding the displacement transmissibility in vehicle design. By analyzing the system's response to different road surface scenarios, we can optimize the suspension system to minimize unwanted vibrations and improve the ride comfort. This involves selecting appropriate values for the spring constant, damping coefficient to achieve the desired transmissibility characteristics. In conclusion, we successfully calculated the displacement amplitude of the vehicle by applying the principle of forced vibration with base excitation. The problem demonstrates how these concepts can be used to analyze and design real world systems involving vibrations. Imagine a washing machine during its spinning cycle. Suddenly, it starts vibrating violently, shaking, and threatening to walk across the floor. What's happening? Likely, it is a case of rotating unbalance. What is the rotating unbalance? It is here the mass unbalance inside the washing machine drum. The wet laundry isn't perfectly distributed. There is a heavier clump on one side. This is the unbalanced mass. Think of it as a tiny weight offset from the center of rotation by a distance e. The rotation is going to be, that is, the drum spins with an angular velocity omega. This unbalanced mass experiences centrifugal force. This force tries to fling the mass outwards, creating a pull that changes direction as the drum rotates. This changing force is what causes the vibration. This the equation of motion, that is mx double dot cx dot plus kx equal to m e omega square sine omega t. This captures exactly the mass imbalance phenomena. Let's see what is this. Mx double dot, the machine's inertia resistance acceleration. Cx dot, damping dissipates energy, reducing the vibration. Kx, machine stiffness, that is springiness, resists the displacement, whereas this me omega square sine omega t is the forcing function representing the total unbalance. The me omega square is the magnitude of the centrifugal force, and sine omega t indicates its sinusoidal variation with time. The machine doesn't just vibrate at any amplitude. The image shows the steady state response of the system. That is, the x of t is x sine omega t minus pi. The machine vibrates with a sinusoidal motion at the same frequency as the drum rotation, but with the phase lag phi. Also, we have to see that amplitude x is possible to calculate using this equation. It also once again depends upon mass, eccentricity, rotation speed, and machine's mass, stiffness, and damping. Phase angle indicates how much the machine vibration lags behind the rotation of the unbalanced mass. Let us see. That is, a common problem in many rotating machines is rotating unbalance, which include engines. Unbalanced crankshafts or flywheel cause vibrations. Turbines. Imbalances in turbine blades can lead to catastrophic failures. Fans and blowers. Unbalanced impellers cause noise and vibration. So, understanding rotating unbalance is crucial for designing and maintaining rotating machinery. By carefully balancing rotating components and incorporating damping, we can minimize vibrations, improve performance, and prevent failures. This image provides a fundamental mathematical framework for understanding and addressing this important issue, that is rotating unbalance. Now, let's delve into the mathematical concepts of the rotating unbalance. That is, we are having the equation of motion of a system with rotating unbalance can be described by the equation, that is mx double dot plus cx dot plus kx equal to me omega square sine omega t. Just now we seen in the previous slide what is the meaning of mx double dot. Can we remember that? It is nothing but it represents inertia of the system. Then what is cx dot? It is damping force like shock absorbers. What is Kx? Stiffness of the system like a spring resisting displacement. And the right hand side, it is nothing but forcing function. That is the main important drawback. That is the rotating unbalance. M is the unbalanced mass. E is the eccentricity. Omega is the rotation speed. Right. We can able to calculate the periodic vibration. That is, the system responds to the forcing frequency with a vibration of its own, represented by the equation, that is amplitude x with a phase lag of phi. And also we can write in terms of resonance conditions. The amplitude or intensity of the vibration is determined by this formula. Notice the term k minus m omega square. When the rotation speed omega is close to the system's natural frequency, this term becomes small, leading to a large amplitude. That phenomena is called as resonance. The phase angle phi tells us how much the system vibration lags behind the forcing function. The rotating unbalance isn't just a washing machine problem, it affects various machines from engine, turbines to fans and blowers. To mitigate unbalance, engineers use balancing techniques and damping mechanisms. By understanding and addressing rotating unbalance, we can ensure smooth operation and prevent catastrophic failures in the machines. We have seen how rotating unbalance leads to vibration, but how do we quantify the severity of this vibration and understand the system response? This image sheds light on the key factors involved. First, let's talk about damping. Damping is the energy dissipation in the vibrating system, like the friction in a shock absorber. We define the damping ratio psi as the ratio of actual damping C to critical damping Cc. Critical damping is the minimum damping required to prevent oscillations. Mathematically, it is defined as 2 times mass and natural frequency. Damping ratio less than 1 indicates an underdamped system when oscillates before settling. Similarly, there will be overdamped conditions and critically damped conditions. Now let's look at the relationship between the system displacement and the unbalanced ME. The ratio mx by Me represents magnification factor, how much the displacement is amplified due to the unbalance. Here, R is the frequency ratio, operating frequency divided by the natural frequency. The denominator involves frequency ratio and the damping ratio. It is the magnitude of the frequency response function. This graph shows magnification factor in terms of frequency ratio. When dealing with rotating unbalance, let me understanding the damping is very much important to see how the amplitude of vibration is also affecting. Let's see the first observation, that is how the curve on this graph begins at zero amplitude. It means at very low speeds, vibration amplitude is minimum regardless of the damping. However, as we approach resonance, amplitude increases significantly. What is the key takeaway? Damping ratio plays major role in controlling this peak amplitude. Now let's consider the second observation. At very high speeds or frequencies, the amplitude ratio mx by Me is almost unity. This means that the displacement amplitude becomes almost equal to the unbalanced mass effect. Interestingly, at this high speeds, the effect of damping becomes negligible. The system vibrates almost as if there were no damping at all. Now you can see this on the graph where all the curves converge towards unity at high frequencies. This implies that at high operating speeds, the unbalance itself dominates the vibration amplitude and the system's inherent damping as it is little impact. Finally, let's look at the third observation for damping ratios less than 1 by root 2. There is a specific frequency ratio where amplitude ratio reaches its maximum. This maximum point can be found by setting the derivatives x by Me with respect to frequency ratio R to 0. The result, as indicated, it is frequency ratio at which the maximum amplitude occurs. This observation is important for understanding the specific conditions under which the maximum vibration amplitude occurs in lightly damped systems. In summary, damping plays a critical role in controlling vibration amplitudes, especially at near resonance levels. At high speeds, its effect diminishes. Understanding this observation is essential for designing and operating machines with rotating unbalance, ensuring their stability and longevity. Let's see the remaining observations. We have been exploring that impact of damping on vibration amplitude. Let me see what are the remaining observations. The equation tells us that for damping ratios less than 1 by root 2, the maximum amplitude ratio occurs at a frequency ratio greater than 1. This means the peak amplitude occurs to the right of resonance value where R equals to 1. The maximum amplitude ratio itself is given by this formula, which depends on the damping ratio. As you can see, the fourth observation, for damping ratios greater than 1 by root 2, the behavior changes dramatically. In this case, amplitude ratio doesn't reach a maximum. Instead, it increases monotonically from 0 to 1 as R approaches infinity. Observe how these curves rise and steadily without forming a distinct peak. This indicates that for higher damping, system response becomes less sensitive to resonance conditions. The last point, the force magnitude is directly proportional to the unbalance and square of the operating frequency. The term inside the square root involves both the frequency ratio and damping ratio, indicating their influence on the force experienced by the system. Understanding these relationships between damping, amplitude, and force is crucial for beginning. By carefully selecting damping parameters, engineers can control vibration amplitudes and ensure the stability of longevity of the systems. Francis water turbines are essential for generating hydroelectric power. They convert the energy of flowing water into mechanical rotation. However, like any rotating machine, they are susceptible to vibrations caused by unbalance. This image presents a simplified schematic of a Francis turbine and poses a crucial design challenge. This diagram illustrates the key components: water flow from point A into the blade B, causing the rotor to spin. The water then exists at the tail race point C. The rotor, with a mass of 250 kg, is connected to the shaft, which is supported by bearings. The challenge lies in ensuring that the rotor remains clear of the stator during operation. The rotor has an unbalance of 5 kg per mm, meaning the mass distribution is not perfectly uniform. This unbalance will cause vibrations. Further, there is radial clearance of only 5 mm between the rotor and the stator. If the vibrations are too large, the rotor could collide with the stator, leading to damage. The turbine operates over a wide speed range from 600 to 6000 rpm. The challenge is to design the shaft so that the rotor remains clear of the stator at all speeds within the range. The shaft, made of steel, is assumed to be clamped at the bearings and has a length of 1 and 2. Our task is to determine the appropriate diameter of this shaft. For simplicity, we will assume damping is negligible. This means we are focusing solely on the stiffness of the shaft to control the vibration amplitude. In essence, we need to find shaft diameter that will provide sufficient stiffness to limit the rotor's vibration amplitude less than 5 mm, preventing contact with the stator at any operating speed. To solve this, we will need to analyze the shaft's deflection under the influence of the unbalanced force. We will use principles of vibration analysis and beam deflection to determine the record shaft diameter. Let me start solving the given problem. That is, to ensure the smooth operation of Francis water turbine, we need to analyze vibration amplitude, frequency characteristics. This the equation gives us the amplitude of vibration denoted by x and the phase angle denoted as phi. The amplitude depends on the unbalanced mass me, the operating frequency and mass of the rotor. It is represented as capital M, the stiffness of the shaft K, and the damping coefficient C. The phase angle indicates the log between the forcing function and the response. To determine the maximum amplitude, we can simplify the equation by setting the damping coefficient C to 0. This is because the damping reduces the amplitude, so the maximum amplitude occurs when there is no damping. By setting C to 0, we arrive at the simplified expression for maximum amplitude. We can further simplify the equation of expressing it in terms of frequency ratio, which is operating frequency divided by the natural frequency omega n. This form is often more convenient for any kind of analysis. Now, let's calculate operating frequency range. The turbine operates between 600 and 6000 rpm, and the crane will operate for 20 pi to 200 pi radius per second. And next, we will calculate natural frequency. The natural frequency is given by the square root of k by m. We know the mass of the rotor is 250 kg. Therefore, the natural frequency is 0.625. We are determining the shaft stiffness for safe turbine operation. In our analysis of the Francis water turbine, we are aiming to determine the record stiffness of the shaft to prevent the rotor from colliding with the stator. The solution demonstrates that we can able to calculate stiffness for two critical operating speeds. Recall that we derived this equation for the maximum amplitude of vibration by assuming negligible damping. This allows us to focus slowly on the stiffness of the shaft to limit the vibration amplitude. Let's first calculate where the operating frequency is 25 radians corresponding to the lower end of the operating range. We know that the maximum allowable amplitude is 0.005 meters, otherwise 5 millimeters. To maintain clearance between rotor and stator, we substitute the known values into the equation. The unbalance will be, we will get it. In the first scenario, the operating frequency we can substitute as 20 pi. After simplifying, we can get the stiffness of the shaft of the turbine is 10 into 10 to the power of 4 pi square. Similarly, as we discussed earlier, we can also calculate for the another operating frequency 200 pi. Let me solve for k, that the required stiffness at the operating speed is 10.04 into 10 to the power of 6 pi square newtons per meter. As again, we can substitute the known values and we can able to calculate for some other natural frequency. That is, as present, we calculated the two stiffness values and we see the significant difference is there. At higher operating speed, the record stiffness is two orders of the magnitude greater than at the lower speed. This highlights the importance of considering the entire operating range when designing the shaft. To ensure the rotor remains clear of the stator and at all operating speeds, the shaft must be designed with the highest stiffness value. This will guarantee that the vibration amplitude stays within the allowable limit throughout the turbine's operational range. The final step, let me calculate the shaft diameter of the Francis turbine. In the earlier slide, we calculated the stiffness. Now, let me calculate the stiffness for the cantilever beam, which is very much essential for supporting the shaft at the bearings. It relates to the stiffness of the Young's modulus of the material, moment of inertia of the shaft cross section, and length of the shaft. The moment of inertia I for a circular cross section is given by pi d power 4 divided by 64, where d is the diameter of the shaft. Substituting this into stiffness equation, we can able to get it. Now we rearrange this equation to solve for the diameter d. We know that the stiffness from our previous calculation, length of the shaft and Young's modulus for steel. We substitute these values into the equation. The stiffness is K is 10 to the power of 4, 10 minus power 4 newtons meter. The length of the shaft is 2 meters. Young's modulus for the steel is approximately 2.07 10 to the power of 11 pascals. After performing the calculations, we find that diameter of the shaft is approximately equal to 0.127 meters, otherwise 127 millimeters. The diameter will provide the necessary stiffness to ensure the rotors remain clear at the stators for all operating speeds. In conclusion, by using the stiffness value calculated earlier and the material property of the steel, we can determine the required shaft diameter for the Francis water turbine. That is, for the given parameters, it is 127 mm. This design will help prevent rotor-stator contact and ensure the safe and efficient operation of the turbine. Today, we explored the dynamic response of damped systems under two distinct types of excitation, the harmonic motion of the base and rotating unbalance. We saw how a system reacts when its base is subjected to sinusoidal motion leading to forced vibrations. We also seen the effects of rotating unbalance, common issue in machineries, and how it reduces vibration due to the eccentricity. In both scenarios, the critical role of damping acts as a crucial role in mitigating the amplitudes of vibrations, particularly near resonance, ultimately contributes to the stability and longevity of the mechanical systems. Understanding these two types of dynamic responses and influence of damping is essential for engineers in designing and analyzing systems that operate under various excitation conditions. This knowledge allows for development of effective vibration control strategies, ensuring optimal performance and reliability. Thank you.